Welcome back to Computer Lessons.
Stop looking up when you hear the cloud. The internet does not live in the sky. It lives underground, buried in dirt, and deep on the cold, dark ocean floor. It is not magic. It is the largest, most expensive physical machine humanity has ever built. Today, we dismantle the marketing myths and expose the raw iron, glass, and copper infrastructure that makes this video possible. We spent 15 lessons building a computer, optimizing its brain, memory, and peripherals. But an isolated machine, no matter how powerful, is just a calculator until it connects to the hive mind. To understand this, realize that the internet is essentially a wire. It is a tangible physical connection, linking your machine to a server in a dark room halfway across the world. The backbone of this machine consists of submarine cables. Right now, hundreds of cables, barely the thickness of a garden hose, snake across the bottom of the Atlantic and Pacific Oceans. These are not satellite signals. Over 99% of international data travels through these underwater wires. Satellites are simply too slow for the modern web, so we rely on glass. Inside these cables are hair-thin strands of glass called optical fibers. We shoot lasers through them, flashing light billions of times per second to represent digital data. This is the speed of light trapped in a glass tunnel, bouncing off walls via total internal reflection. However, even light gets tired traveling thousands of miles through the ocean depth. To fix this, engineers install massive repeaters every 50 to 100 kilometers along the seabed. These devices intercept the fading light signal, boost its power using shore-supplied electricity, and blast it forward. If a repeater fails or a ship dragging its anchor snaps the cable, entire countries can lose connectivity instantly. This cable network is owned by industry titans known as Tier 1 Internet Service Providers. Companies like AT&T, Verizon, and Lumen own the physical roads data travels on. They do not pay for access because they are the internet. They peer with each other, agreeing to pass massive traffic between their networks for free. Below them are Tier 2 providers, usually large national telecom companies like Comcast or BT. They pay the Tier 1 giants to access the global backbone but peer with each other to save costs. Finally, at the bottom are Tier 3 providers, the local ISPs you pay monthly to run a cable into your house. These networks connect at physical locations called Internet Exchange Points, or IXPs. Imagine a building filled with blinking routers and yellow fiber cables. This is where networks handshake. It is where Netflix hands movie data to your local ISP for delivery. Without these physical meeting rooms, the internet would be a fragmented mess of isolated networks. Now, let's look at where data lives. The data center. When you save a file to the cloud, you send it to a fortress, consuming the electricity of a small city. These facilities are filled with rows of server racks, which are essentially powerful, screenless computers stacked on top of each other. These servers generate incredible heat, the greatest enemy of the data center. Engineers use hot aisles and cold aisles to manage airflow efficiently. Industrial cooling works 24/7 to keep silicon chips from melting. If cooling fails, servers shut down and millions lose access to emails and bank accounts. Security here is stricter than at most military bases. There are biometric scanners, man traps preventing tailgating, and armed perimeter guards. They use massive diesel generators and battery banks to ensure the internet stays alive, even if the city grid collapses. Your cat video is literally guarded by men with guns. We must distinguish between the internet and the World Wide Web. The internet is the infrastructure, the roads, cables, and routers we just discussed. The web is the traffic driving on those roads, the collection of HTML pages and browsers built on top of the infrastructure. You can use the internet without the web, like sending an email or playing multiplayer games. The web was invented by Tim Berners-Lee in 1989, decades after the first networks. He created the protocols allowing us to click links and jump seamlessly from server to server. Let's trace a single click from your home to a server. You click a link, and your computer sends a request to your router, converting the digital signal for the modem. This travels over the last mile, usually copper or fiber, to your ISP's local distribution node. From there, it jumps onto the regional fiber ring to the nearest internet exchange point. If the server is overseas, your signal routes to a coastal landing station. It dives into the ocean, flashes through glass at light speed, and emerges on a different continent milliseconds later. It travels through that country's backbone, down to their regional ISP and into the data center. The server processes the request, finds the data, and sends it all the way back along the same path. This entire round trip spanning thousands of miles happens faster than a blink. However, distance matters because the speed of light is finite. This delay is called latency, or ping. If you are in London playing a game hosted in Sydney, you experience lag because light physically travels halfway around the world. To combat this, companies use CDNs, or content delivery networks. Instead of hosting a website in one place, they clone it to hundreds of servers globally. When watching YouTube, you aren't streaming from California. You are likely streaming from a CDN server just miles away in your city. This physical reality makes the internet vulnerable to physical attacks. If a ship cuts strategic undersea cables, entire continents can be isolated. We saw this when an anchor cut cables connecting Tonga, leaving the nation in digital darkness for weeks. Redundancy is the only defense against physical failure. The internet is a mesh network, offering multiple paths from A to B. If one path breaks, routers automatically calculate a detour, sending data the long way around to ensure arrival. Routers are the traffic cops of this chaotic system. They sit at every intersection, reading data addresses and deciding which wire to use next. We will dive into their decision logic later, but physically they are computers optimized for sorting. The scale of this infrastructure is hard to comprehend. We wrap the planet in glass threads powered by burning coal and splitting atoms just to send emojis. It is a testament to humanity's desire to connect and overcome physical geography. So when your internet is slow, don't just blame the cloud. Remember the physical journey through copper, glass, and salt water. Remember the lasers, repeaters, and massive air conditioners fighting thermodynamics to keep the connection alive. We have established the roads and warehouses of the digital world. But roads are useless if cars lack license plates and buildings lack addresses. We need a way to uniquely identify every device on this massive network. In the next video, we unpack the mystery of IP addresses and packets. We will learn how the digital postal system works, explaining the vital difference between IPv4 and IPv6.
Tell me in the comments, did you know the internet is mostly underwater cables, or did you think it was all satellites? I am curious to hear your thoughts. If you found this explanation helpful, please hit the like button and subscribe to Computer Lessons. Don't forget to click the bell icon so you don't miss our next class. Thanks for watching and keep learning.